Time is an illusion. Quantum physics proves it. The decision was already made before anyone pressed the button. The detector blinked, the interference vanished, and only later did the experimenter choose how the photon should have behaved. Get this, our choice seemed to echo backward, rewriting what the past looked like. That's the quantum glitch. It breaks the clock face story we live by. Delayed choice, entanglement, indefinite order. If time is a lie, causality and free will wobble. But we're not going on vibes, we're going into labs. Real experiments, no fluff. To understand the glitch, we need to go back to a simple beam of light, then jump forward to where reality bends. The choice that echoed backwards, delayed choice. John Wheeler didn't start with hardware. He started with a question. What if you decide how to measure a photon after it's already past the point where that decision should matter? In his thought experiment, a single photon travels through an interferometer, two possible paths that can create an interference pattern if both paths remain indistinguishable. But there's a catch. You can insert or remove the final beam splitter late, so late it feels like the photon should have already chosen a path. The result. The pattern you see depends on a choice made at the last moment. That decision looks like it reaches backward. Now move from chalkboard to lab bench. Modern versions use fast optical switches and random number generators that decide, after the photon is inside, whether the interferometer is closed, paths recombine, allowing interference or open, paths separated, revealing particle-like which path behavior. When the interferometer is closed, you get the smooth interference fringes that say the photon behaved like a wave, exploring both paths. When it's open, the fringes vanish and detections pile up in a way that says the photon took a path. The weird part is timing. The setting is chosen so late it looks like the future choice dictates the earlier behavior. Here's why this moment matters. Everyday logic says causes come first and effects follow. You flip the switch, then the light turns on. If the light pattern responds to a switch flipped after the photon's critical moment, causality feels shaky. For real people in the lab, this isn't a word game. It's their equipment returning data that doesn't fit the story of tiny billiard balls tracing tiny lines through space. If that story fails our sense of I act, then the world response starts to wobble. What actually happened is painfully precise. A photon source fires. The photon hits the first beam splitter, putting its path into a sewer position. It travels down both arms, phases accrue, and then, just before it would recombine, an ultra-fast device, sometimes driven by a quantum random number generator, decides whether to insert the second beam splitter. If inserted, the two paths recombine, and the phase difference decides which detector clicks. If removed, there's no recombination. The detectors reveal which path. The experimenters verify space-like separation or tight timing, so the choice cannot be known, in time, by the photon's earlier segment. The immediate impact, outcomes match the late choice. Close the interferometer, you recover interference. Open it, you don't. What didn't happen, recombination or path marking, still matters to the statistics. It's as if the world only commits to wave-like or particle-like when you pose the question, even if the question is asked after the photon passed the fork. That's the glitch. The meaning of before and after isn't doing the work we thought. In labs and hallways, the arguments get sharp but focused. One camp says retrocausality might be on the table. Maybe future measurement settings correlate with earlier outcomes in a way that looks like influence backward in time. Another camp, the no trajectories crowd, says the mistake is assuming the photon had a single path story waiting to be read. In standard quantum mechanics, there aren't definite paths until you force that description with a measurement that makes them definite. No need for signals to the past. Just don't assign a narrative the math doesn't support. And the guardrails matter. Nobody in these labs claims you can send a message to your former self. The correlations don't let you encode information into the past. You can't pick settings to force a retroactive sentence of Morse code into yesterday. When you look only at the early detections, before sorting by the later choice, they don't spell anything. The strange behavior only shows up when you compare joint data, detection outcomes paired with the late settings. The past doesn't change. The story you can consistently tell about it does. Meanwhile, something else is happening in parallel across different groups. Delayed choice quantum erasers add a further twist. They tag witch path information with entanglement, then later erase or reveal that information. If witch path information is made unknowable, interference patterns reappear in the sorted data. If witch path information is retained, interference vanishes. Again, the crucial piece is that the decision to erase can happen after the photon hit the screen. It's the availability of information in the joint correlations that decides the pattern, not a fixed tape of history. Here's the turning point. The delayed choice experiments don't only tease us with paradox, they force a cleaner language. The photon doesn't carry a little diary of its journey, asking which path did it really take. When the setup was tuned to produce interference is like asking which note a chord really is. The answer depends on what you measure. The late choice doesn't reach back to flip a switch in yesterday's hardware. It decides which properties become part of the record you can build without contradictions. In the aftermath, something essential changes for the people involved. Students walk in thinking physics is about tiny objects with tiny tracks. They walk out knowing physics is about correlations between preparations and measurements. One detail proves crucial later. The order of events you assumed would explain everything doesn't rescue you here. You can try to shuffle before and after, but the predictions don't care. And that's our bridge. While delayed choice bent time locally, a deeper fracture lived in entanglement, where two particles act as one system, and time ordering stops being a helpful excuse. Entanglement's no-time contract. While that was twisting minds in one lab, across town, another team was doing something even stranger, splitting a pair of photons so they were born entangled, then sending them in opposite directions at high speed. Each side gets a polarizer with a setting chosen on the fly, sometimes by a fast random number generator, sometimes by light from distant stars. When they compare notes later, the numbers refuse to fit any story built from local properties and fixed time order. The data say the pair behaved like one system, no matter the miles between them. Here's why this moment matters. If two detectors separated by city blocks show correlations that defy any mix and match of pre-agreed instructions, then our everyday picture cracks. We want to say a measured first, then B responded, or B first, then a responded. But relativity lets different observers disagree on who was first. If the correlations are real and robust, and they are, then before and after can't explain the link. The stakes are personal. Researchers had to decide which part of their intuition to let go. What actually happened is a sequence perfected over decades. Early Bell tests had loopholes. Maybe the detectors weren't efficient enough, or the settings weren't truly independent. Teams closed them, one by one. Elaine Aspect's experiments in the 1980s switched settings fast so no signal could sneak between the stations in time. Later, groups in Delft and Vienna boosted detection efficiency so missing events couldn't bias the sample. Then came satellite links, pushing entanglement over hundreds or even thousands of kilometers. And then a bold flourish. Cosmic Bell tests that used photons from distant quasars to pick the measurement settings, pushing any would-be conspiracy back billions of years. The impact was unmistakable. The correlations violated Bell inequalities, mathematical limits any local realistic theory must obey. The world doesn't fit a model where each particle carries hidden instructions that say, if measured this way, return that result, all without influence from the other site. Try to fix it by saying, fine, A happened first, and relativity shrugs. Some observer sees B first. Flip to B caused A, and another observer disagrees. The pattern stays put, while time order slides underneath it. Here's the key insight that sank in slowly. Before and after aren't the levers that make the data work. The joint outcomes arise from the entangled state and the pair of settings together. If you only look at A's results without B, they look random. Same for B alone. Put them together with the chosen settings and the structure appears. It isn't a message sent faster than light. It's a constraint woven into how the joint system responds to the pair of questions. Walk the hallways and you hear the debates in plain words. Some argued realism had to go no definite values before measurement. Others wanted to keep realism but give up locality or give up the independence of settings. Anton Zeilinger leaned into the experiments, trust what the data say and refine the questions. Meanwhile, theorists sharpened the logic. You can hold on to causal order as a comfort blanket, but the correlations don't need it. Put A first, put B first, alternate them. Same predictions, same violations. We need guardrails, so let's set them clearly. You can't use entanglement to send a signal faster than light. The no-signaling theorem isn't a suggestion, it's baked into the formalism and the data. A alone sees noise. B alone sees noise. Only after the fact, when they compare, does the pattern click into place. So no, you can't warn a friend across the ocean instantly, and you can't rescue your past self from a bad decision. The correlations are strong and stubborn, but they don't carry usable messages. Meanwhile, something else was happening in new experiments that tested timing assumptions directly. Researchers engineered space-like separation so that, according to relativity, neither station could be in the other's past light cone when the settings were chosen and the outcomes recorded. They even randomized the settings with cosmic light to weaken the freedom of choice loophole. Each step tightened the vice around classical explanations. The correlation stayed, calm and immovable, as if time order were just background scenery. This was the moment everything changed for many working physicists. Entanglement wasn't a quirk, it was the operating system. Pairs, sometimes triplets and clusters, behaved as single wholes, and the language of separate parts responding in sequence felt clumsy. You could try to force a story where one side influences the other in time, but you'd be choosing a frame that another observer would deny. The better language was simpler. The outcomes are jointly constrained. In the aftermath, the field pivoted from "is entanglement real?" to "what can it do?" Quantum cryptography, teleportation, and distributed sensing all grew from taking the correlation seriously. But the philosophical bruise lingered. If time order doesn't help, what is the order that matters? That question led a few brave teams to a radical test. Set up processes where there isn't a single definite A then B or B then A at all. Let the order itself go quantum. If entanglement showed that distance can fade, maybe sequence can melt too. And when they tried it, the results hinted that before and after might not be fundamental. When order melts, quantum switch and indefinite causality. While that was happening in entanglement labs, a smaller group tried something bolder. Stop assuming there's a single order to events at all. Here, S the stakes. If the order of operations can be indefinite, A before B and B before A at the same time, then time can't be a global stage. It becomes context. And if order itself goes quantum, our old crutch for causality falls away. What actually happens starts with a clever device called the quantum switch. Take two operations, call them A and B. Think of them as black boxes that transform a photon's polarization. Classically, you'd pick an order. The photon goes through A, then B or B, then A in the quantum switch. You put the control of the order into a superposition. A separate control qubit determines whether the target photon experiences a right arrow B or B right arrow A, and that control qubit isn't set 2 or 1. It's in both. The result is a process where the target system undergoes A before B and B before A, coherently superposed, so long as the control remains coherent. Researchers realized they needed new language to describe this, because standard quantum circuits assume a fixed temporal order. Enter process matrices, a framework that lets you talk about correlations between operations without presuming there's a single, underlying sequence. Within that framework, some processes are causally separable. You can explain them as a mixture of definite orders, and others are causally non-separable. No mixture of a right arrow B and B right arrow A reproduces the statistics. The quantum switch lives in that second category. Teams built photonic versions using interferometers. In one arm, the photon sees a then B. In the other arm, it sees B then A. Interference between the arms certifies the superposition of orders. The immediate impact wasn't just conceptual fireworks. There were practical payoffs. Certain information processing tasks get easier when you don't lock the sequence. For example, distinguishing whether two unknown operations commute or not. Classically, you need to test both orders. With an indefinite order, you can do it in a single shot with higher success probability, because the device explores both sequences at once and the interference encodes the answer. People called it a causality glitch that helps you compute. And you should have seen the human reactions. Some were stunned that causality could be a resource. Others were cautious. Is this just a trick of labeling? Experiments pushed back on the skepticism. They measured causal witnesses, observables designed to detect causal non-separability the way entanglement witnesses detect entanglement. When the witness goes negative, no classical mixture of orders can explain the data. Multiple groups saw those signatures, with better stability and tighter error bars each year. Guardrails matter here too. No, this isn't time travel. The lab doesn't let you send your future self a note. The device doesn't produce contradictions or grandfather paradoxes. What it shows is that, for some quantum processes, nature doesn't assign a single, global what happened first that everyone can agree on, even in principle. The order is entangled with the control system, and until you measure that control, before and after are not settled facts. Meanwhile, something else was happening in theory that sharpened the stakes. If you allow indefinite order, you need to rethink what causal relations mean. Without a fixed sequence, we stop defining cause as earlier influences later. Instead, we define it in terms of constraints among operations, which interventions can change which statistics. That's a different backbone for causality, one that doesn't rely on a universal time parameter. It fits suspiciously well with what we saw in entanglement and delayed choice. The data care about relations, not about a master clock. Here's where it gets useful fast. Communication complexity tasks, where two parties try to compute a function with minimal communication, can get a boost with indefinite order. Query problems, channel discrimination, even certain metrology protocols all show advantages when the lab can superpose sequences. The glitch isn't just philosophical, it's operational. Researchers learned to protect the control qubit's coherence long enough to extract those gains, an engineering challenge that turned metaphysics into hardware. One micro-story sticks. A young postdoc watched the interference fringe from the switch drift across a screen at 3 a.m., then hold steady as the causal witness dipped into the non-separable region. He didn't cheer. He just muttered, "So it's real," and wrote the time in his notebook, then scratched out time and wrote readout. But there was one problem. If order is indefinite, what anchors change? What makes events more than floating relations on a blackboard? The experiments tell us sequence can melt locally, yet our lives feel ordered. Meetings start, coffee cools, signals arrive. To understand why that feeling persists even when microorder flickers, we need a bigger frame. While that was happening in the photonics lab, relativity was waiting with a harder truth. There is no universal now to anchor any of this. Enter the block. The block universe you can't escape. 3 days earlier on a train platform, 2 clocks ticked in perfect sync until the train moved. One passenger said 2 distant lightning strikes were simultaneous. A person on the platform said they were. Both were right. That simple disagreement, who's first, who's second, wasn't a nitpick. It was Einstein's quiet demolition of a universal now. If simultaneity depends on motion, then there's no single slice of the present that everyone can share. Here's why that matters for us. We like to think time is a river that sweeps everything forward. Relativity replaces the river with geometry. Events are points in a 4-dimensional spacetime. Your life is a path, a world line weaving through that geometry. Clocks don't measure a global tick. They measure the length of their own paths, proper time, like measuring a route on a map. 2 people can disagree about lengths of segments and angles, but the geometry keeps them honest. There's no master metronome in the background, just paths and intervals. What actually happens on the ground is almost mundane. GPS satellites carry atomic clocks. They orbit fast and high, so relative to us, their time flows differently. Engineers correct for special relativity, motion slows clocks, and general relativity, gravity speeds them up higher up. The numbers match the equations and your phone finds your location. No drama, just a daily admission that time is geometry, not flow. If there were a universal now, we wouldn't need frame-dependent corrections. The system would just agree. It doesn't. Now remember, this is relativity's tough love. Carve spacetime into now slices however you like. The physics doesn't prefer one slicing over another. Some choices make calculations easier, but none are sacred. In that picture, past, present, and future all exist as parts of the block, like different frames of a film that already sits on the reel. You experience the frames in order because your brain is a machine that writes and reads records along one world line. The block doesn't move, you do through correlations. Here's the human note that lands hard. In 1955, after his friend Michel Besso died, Einstein wrote that for those who understand physics, the distinction between past, present, and future is a stubbornly persistent illusion. He wasn't sneering at grief. He was reporting a consequence of the geometry. The loss felt immediate to him, but the theory put both men's world lines into a single structure where now is a choice, not a fact of the universe. And yet we feel becoming. Coffee cools, children grow, a song starts and ends. That tension sits at the center of today's puzzle. Quantum mechanics seems to have events, measurements, outcomes, updates. Relativity shrugs and says, show me the invariant. So what bridges them? One promising idea is that what feels like flow is a pattern of correlations across the block. Records, brain states, ink on paper, bits on a drive, link earlier slices to later ones. The asymmetry we feel isn't a moving present. It's the direction in which reliable records accumulate. Meanwhile, something else is happening when you zoom out. The block doesn't tell you which histories are allowed. Dynamics and constraints do. Field equations carve out which shapes of blocks are consistent. Initial or boundary conditions pick which block we inhabit. And the content of the block, matter, fields, entanglement, supplies the correlations that masquerade as flow. When your brain updates, it writes a stable record pointing backward. There are no records pointing forward because, for reasons we'll face later, the universe started in a low entropy state that made backward-pointing records cheap and forward-pointing ones fragile. Here's the turning point for our story. If relativity erases a universal now, then quantum weirdness about order isn't an outlier. It's a local echo of a bigger fact. Entanglement and indefinite order told us that before and after aren't fundamental levers. The block tells us there was never a universal lever to begin with. Causality, then, can't be earlier pushes later in some absolute sense. It has to be relational. Constraints among events that fit together without contradiction, independent of any chosen slicing. But there's a catch you can't ignore. A block picture alone risks fatalism. If everything already exists, where do choices live? The answer isn't mystical, it's structural. Choices are macroscopic processes, brain-body environment dynamics, that select stable records consistent with the block's laws and boundary conditions. From within the block, agents are subsystems implementing computations that steer which correlations become part of their branch of records. The feeling of deciding comes from writing new records that didn't exist on your earlier slice. One micro story. A graduate student misses a bus and stumbles into a seminar on indefinite causal order. That detour becomes the first line in a paper that changes her career. In the block, both paths exist. In her world line, one set of records takes hold. She doesn't change the future. She becomes the future that contains those records. So the block you can't escape isn't a jail, it's the stage. Time isn't a universal flow. It's the geometry of relations plus the growth of records. But a stage doesn't write scripts. Constraints do. And one controversial constraint tries to save locality and realism by tying our choices to the rest of the block so tightly it hurts. If a universal now is gone, maybe free settings are gone too. That uneasy possibility has a name, and it's waiting right around the corner. Superdeterminism versus freedom, the uncomfortable out. While that was happening in the block, another idea crept in through a side door and made everyone uneasy. Bell's theorem leaves you with a harsh menu: give up locality, give up realism, or give up the independence of measurement settings. Most people surrender locality or realism in some form. A smaller group points to the third option and says, what if the settings were never free to begin with? That's superdeterminism, and the stakes are personal, because free settings are our stand-in for free will. Here's the pitch in plain language. In standard Bell tests, we assume the random number generators that pick the measurement angles are independent of the hidden variables that determine outcomes. Superdeterminism denies that assumption. It says the entire experiment, particles, detectors, randomizers, even the choice to flip a setting, is correlated from the start by deep, deterministic initial conditions. If that's true, the observed violations of Bell inequalities don't force non-locality or indeterminism. They just reveal a hidden coordination we mistook for independence. What actually happened in the community looked like a slow, reluctant debate. Gerard T. Hooft, a Nobel laureate known for hard-nosed physics, argued that a deterministic substrate might underlie quantum mechanics. In that view, the wave function is a bookkeeping device for ignorance, and the apparent randomness comes from coarse graining over a deeper, clockwork layer. The controversial move is accepting that our measurement choices are not statistically independent of the systems we probe. Critics called it a cosmic conspiracy, nature arranging every setting and every hidden variable to line up just so, across billions of years, to fool us into thinking action at a distance is real. Impact of taking this path is clear. You save locality, no spooky influence leaping across space. You save realism, outcomes reflect underlying properties, but you pay a philosophical price. You weaken the very idea of intervention. If every time you think you could have set the knob differently, the deeper state of the universe already baked in that you wouldn't, then could have becomes decoration. For many, that's too heavy a cost. For others, it's a fair trade to keep physics local and concrete. People didn't just argue, they tested assumptions. Cosmic Bell experiments tried to push the independence of settings as far as possible. Instead of trusting electronics on the lab bench, teams used light from distant quasars to choose the angles. Those photons left their sources billions of years ago. If superdeterminism is right in the strong conspiracy sense, then the correlations had to be arranged since before those photons began their journey. The guardrail here is honesty. Even that doesn't logically rule out superdeterminism. It just makes the required coordination stretch to absurd scales. Meanwhile, something else was happening in the theory space. A few researchers asked, can we make superdeterminism scientific instead of a verbal escape? That means models with equations that predict new, testable deviations from standard quantum mechanics. If the deep dynamics create subtle statistical skew, maybe we'd see tiny violations of no signaling or small, setting-dependent biases in Bell-type data. So far, robust experiments keep returning the same answer. Quantum predictions hold, no extra patterns. Superdeterminists respond. Our models can match those constraints, which keeps the conversation alive but also pins them to an ever-narrowing corner. Here's the human angle that's easy to miss. Experimentalists hate loopholes because loopholes make their work look like stage magic. They've spent decades closing detection inefficiencies, timing leaks, and locality gaps. The freedom of choice assumption is the slipperiest one, because you can't prove independence in an absolute sense. You can only push it outward to stars, to quasars, to the cosmic microwave background if you dare. The further you push, the more the conspiracy has to include. That cumulative pressure is a character in the story, a quiet force that shapes what most physicists consider reasonable. Let's set guardrails so we don't strawman anyone. Superdeterminism doesn't mean nothing matters or ethics evaporates. Determinism has lived in physics before, and people made choices, built bridges, and went to jail just fine. The issue is narrower: whether the statistical independence assumption used in Bell's argument is physically valid. If it's not, Bell's logical squeeze relaxes. But relaxing a squeeze isn't the same as explaining the data. A convincing superdeterministic theory has to do at least what quantum theory already does: predict outcomes with high precision, and ideally more. There's a micro-story that lands the discomfort. A graduate student designing a new Bell test writes independent RNG in her notes, then pauses. She laughs, crosses out independent, and writes independent enough. That's the whole fight in 2 words. How much independence is enough? In the lab, enough means no known causal link. In superdeterminism, known is the trapdoor. Here's the turning point for our arc. If superdeterminism were compelling and predictive, many would swallow the cost to keep locality and realism. But right now, it feels like a broad permission slip, an all-purpose explanation that rarely risks a hard, falsifiable bet. Meanwhile, the glitch we're tracing doesn't need that permission slip. The delayed choice and entanglement data already told us that before and after aren't fundamental levers. Indefinite order showed sequence can be a quantum resource. If not superdeterminism, then maybe the real hinge is closer to home, the act of measurement itself. What if the glitch lives where outcomes become records? The measurement that makes reality, Copenhagen to QBism. While superdeterminism hovered like a storm cloud, the working labs kept bumping into a simpler, sharper hinge. Outcomes arrive when you measure. Here's the stake: if outcomes aren't definite until they're registered, then before and after blur at the edges, because the very thing that becomes the past is defined by what makes it into the record. That's where the Copenhagen tradition planted its flag, and where modern agent-centered views like QBism pushed further. What actually happened, historically, starts with a divide that experimenters still live with: the quantum world described by wave functions and operators, and the classical world of apparatus and readouts. Niels Bohr insisted the apparatus must be described in ordinary language, with classical concepts, so results can be communicated and checked. He didn't say the apparatus is fundamentally classical. He said it must be treated that way for physics to function as a shared activity. The cut between system and apparatus isn't carved in stone. It's wherever you place the line to model a concrete experiment. In that picture, measurement isn't peeking at a per-written answer. It's an interaction that produces a stable outcome, an irreversible mark in the macroscopic domain where amplification, decoherence, and practical irreversibility live. You prepare a state, couple it to a meter, and when you read the meter, you update your description. The math calls it collapse. Probabilities jump from fuzzy distributions to sharp events. The lab calls it data: a click, a spot, a number. The conceptual point is modest and brutal. The theory gives probabilities for possible outcomes. The measurement is where one of them becomes fact. The impact on time talk is immediate. If the click is what fixes what happened, then the past you can consistently narrate is the past consistent with that click and everything else recorded. Ask which path the photon really took before the apparatus was set to reveal paths, and you're asking for a fact the world didn't supply. Bohr's followers learned to refuse the question, not out of evasion, but because experiments teach you to ask only what can be settled by a record. That's a hard habit to learn, and once learned, it reshapes how you talk about cause and effect. Meanwhile, something else was happening in the late 20th and early 21st centuries. A group of physicists reframed quantum states as personal betting odds. Quantum Bayesianism, QBism, says the wave function isn't a physical field waving in space. It's an agent's catalog of expectations for her own experiences when she takes actions on a system. A measurement isn't the universe collapsing. It's the agent updating her beliefs upon receiving a new experience, using the Born rule as a normative guide for consistent probability assignments. Here's the key insight QBism injects into our timing problem. If quantum states are about an agent's expectations, then time in the formalism is a parameter that orders her actions and updates. There's no cosmic clock tick that collapses anything. There's an agent choosing an intervention, assigning probabilities, and then updating when the result arrives. The flow you feel is the flow of information relative to you. That doesn't trivialize physics, it grounds it. Predictions still match experiments. Tomography still reconstructs devices. Quantum cryptography still works. The difference is what the symbols stand for. Critics push back. Does this dodge ontology by hiding in subjectivity? Cubists answer that subjectivity is where any probability lives, and that intersubjective agreement arises because agents cohabit the same world, face the same constraints, and can check each other's records. The guardrail is firm. QBism doesn't claim the world is a hallucination. It says quantum theory is a user's manual for agents in the world. Ontology isn't denied. It's decoupled from the way functions roll. The outcomes are real for the agent who experiences them. The rules that guide expectations are universal. Here's a micro story that makes it concrete. A student sets up a polarization measurement and calculates a 70% chance of vertical. The detector clicks vertical. She updates, now her odds for follow-up questions change. Across the hall, her lab partner, who didn't see the click, still assigns 70-30 until the data are shared. When they compare notes, their stories synchronize. The past they can both affirm is the one consistent with the shared record. No mystery message traveled through time. A common world constrained two agents into agreement. Now remember the delayed choice headache. In Copenhagen and in QBism, no one needs retrocausality. The late choice selects which question became meaningful to ask, and the answer becomes a fact when registered. Before that, there wasn't a fact of that specific type. The glitch isn't a violation of causality. It's a warning not to force a single global event order or a pre-existing catalog of properties onto phenomena that only yield definite properties under particular interventions. There's a tension we shouldn't hide. Does this demote time or just reframe it? In these views, time in the equations tracks how systems evolve and how agents plan and update. The flow you feel isn't a cosmic conveyor. It's the unfolding of records as interventions happen. That sits comfortably with the block idea. The geometry doesn't flow, but records pile up along world lines. From the inside, that accumulation feels like a moving now. And there's the bridge to where we're headed next. Some refused collapse, betting that outcomes exist but branch. Many worlds keeps the equations unitary, no special updates, just decoherence carving stable records. If Copenhagen says outcomes are made and QBism says outcomes are experienced, Everett said outcomes are all there, in parallel. If time is a user's parameter here, could it be a structural parameter there? Let's walk into the branches and see how flow becomes an illusion with teeth. Many worlds and the illusion of flow. Walk with Everett for a minute. He looked at the quantum rules and refused to add collapse. Keep the Schrödinger equation running smoothly always. If the math says a system evolves into a superposition of outcomes, then the combined system, object, apparatus, observer, air molecules, everything, evolves into a superposition of macroscopically different records. On one branch, the detector says yes. On another, no. Nothing singular hops in to kill alternatives. Alternatives simply decohere, spread their phases into the environment, so branches stop interfering and act like separate worlds. Here's why that matters for our glitch. If there's no collapse, then when did the outcome happen? Becomes a branch relative question. Outcomes are definite inside a branch because decoherence selects stable, classical-looking records, pointer states, that persist. Globally, the wave function holds all the branches at once. Locally, you only ever experience one. The flow you feel is the steady growth of your branch's records, not a cosmic hand dragging a single outcome forward. What actually happens in a measurement on this view is unitary and mechanical. You start with a system in a superposition and a detector ready to read. They interact. The combined state entangles. The environment, air, photons, the lab bench, soaks up phase information so those entangled components can't talk to each other anymore. That loss of interference is decoherence. You don't need a conscious observer. You need irreversible spread of information into many degrees of freedom, which the world supplies in abundance. From inside any branch, you see a single result and a world consistent with it. The impact lands across scales. Apparent randomness turns into subjective uncertainty. Before you look, you don't know which branch you'll find yourself in. After you look, you're in a branch with a specific outcome and a memory of seeing it. Globally, nothing chose. Branch-relative observers report choices because their memories are records in a single decohered history. That fits our earlier theme. Facts live in records and records grow along world lines. Many worlds just says the growth happens across countless, non-interacting histories in parallel. Meanwhile, something else is happening that makes this more than a word game. Decoherence theory, sharpened by Zherk and others, shows how classicality emerges from quantum dynamics. Pointer states are those that resist entangling into messy sewer positions with the environment. They survive like sturdy melodies amid noise. Redundant imprinting, quantum Darwinism, spreads information about these pointer states into many environmental fragments. Multiple observers can sample different fragments and agree on what happened without disturbing it. Consensus arises because the environment broadcasts select facts. But there's one problem many worlds can't wave away: probabilities. If all outcomes occur, what does 70% chance mean? The Born rule says squared amplitudes set weights, but why should an observer care about weights in a sea of branches? Several strategies exist. Decision-theoretic arguments say a rational agent betting on branch-relative outcomes should weight bets by squared amplitude to avoid guaranteed losses across their future copies. Invariance arguments try to derive Born weights from symmetries of entanglement. Critics aren't satisfied, but the debate lives in the details, not in a quick dismissal. Then there's the preferred basis headache. In a continuous sea of possible decompositions, which branching structure counts as the worlds? Decoherence helps because interactions select pointer bases that are approximately classical, positions, pointer orientations, robust macrostates. The branches aren't arbitrary. They're picked by the dynamics and the environment's relentless monitoring. That selection is approximate and context-dependent, but it's enough to explain why tables look solid and detectors click in stable positions. Here's a micro-story that humanizes the abstraction. A grad student runs a toy model of decoherence on a laptop, a qubit coupled to a bath. She plots the off-diagonal terms in the reduced density matrix and watches them dive to nearly zero. Her advisor says, "That's your collapse." She replies, "No, just decoherence." He smiles. They both know the model didn't add magic. It added a bath, and the bath did the work. Now remember our through line. Delayed choice complicated before. Entanglement ignored distance. Indefinite order melted sequence. Many worlds keeps time as the parameter in the unitary evolution, but moves the becoming into branch-relative record formation. Flow becomes an emergent narrative your brain writes as it updates within a single decohered history. The river isn't out there. It's the stitching of correlated states along your path. That stitching explains why you never meet your other branches. Interference between macroscopic branches is effectively gone because the environment keeps their phases dispersed beyond recovery. Guardrails stay in place. Many worlds doesn't let you signal to your other copies. You can't jump branches or pull information from a parallel you. The theory trades collapse for multiplicity, not for superpowers. It still respects the no-signaling structure and all the lab data we've leaned on. The shock is philosophical. Determinism globally, uncertainty locally. No single timeline, but a web of consistent ones. Here's the turning point. Many worlds still assumes a time parameter in the background to run that unitary evolution. If time itself isn't fundamental, can we tell this story without a master clock at all? That's where quantum gravity leans in. The deepest equation we have for the whole universe writes zero where you'd expect time to sit. Lose the clock, keep the correlations, and watch becoming reappear as a relation, not a tick. The timeless equation, Wheeler-DeWitt. 3 years earlier, in a quiet office with too many chalkboards, a different kind of silence settled over physics. Write the equation for the whole universe and the symbol for time disappears. That's the Wheeler-DeWitt equation, H acting on psi equals 0. No T, no ticking parameter, just a constraint that says the universe's quantum state is stationary. If your gut says, but things change, you've arrived at the puzzle physicists call the frozen formalism. Here's why this moment matters. We've leaned on time as the backbone for every story, preparation, interaction, measurement, record. If the fundamental equation for the universe doesn't have time in it, then the flow we feel can't be fundamental. It has to come from structure inside psi, patterns, correlations, conditional facts, rather than an external clock. That's a hard shift for humans built to count beats and sunrises, but it's the cost of writing one equation for everything. What actually happens in the derivation goes like this. Start from general relativity, where spacetime itself is dynamical, and mix it with quantum mechanics, where states evolve by a Hamiltonian. In relativity, you can slice spacetime into space plus time in many ways. The theory doesn't privilege one. When you quantize that reslicing freedom, time stops being a parameter you feed in from the outside and becomes part of the constraints that physical states must satisfy. You end up with H psi equals, not energy times wave function equals change, but physical states are annihilated by the Hamiltonian constraint. DeWitt felt the weight of that. He worried about how to get motion, planets orbiting, minds thinking, out of a motionless master equation. The answer many reached for was relational time. Don Page and William Wooters proposed a clean idea: split the universe into two parts, a clock and the rest. The total state is static, but when you condition on the clock reading 1 p.m., the rest looks like it's in state A. Condition on 1 p.m., and it looks like state B. Change appears as correlations between subsystems. No external T, just when the clock says this, the system tends to that. For a long time, it lived as a beautiful toy model. Then experiments started poking the edges. Lab groups built entangled clocks out of photons and trapped ions, letting one part serve as a time reference for the other. In careful setups, they showed that conditional states evolve relative to an internal clock even when the joint state is engineered to be globally stationary. These aren't tests of quantum gravity. They're proofs of concept that relational time has experimental teeth. The immediate impact is a new way to say becoming. You don't need a master clock outside the universe. You need subsystems that can play clock for each other, good timekeepers that correlate strongly and predictably with changes in the rest. That picture dovetails with what we've learned about records. A clock isn't special because it touches a cosmic tick. It's special because it writes reliable correlations you can use to order experiences. The flow we feel is the steady update of conditional expectations. Given my watch reads this, my lab notebook should read that. Meanwhile, something else was happening in quantum cosmology. Approximations like the Born-Oppenheimer split let heavy, slow degrees of freedom, the geometry, roughly act as a background against which lighter fields evolve. In that semi-classical limit, an emergent time parameter appears, built from the geometry itself. You get back a Schrödinger equation for matter fields with respect to this WKB time, but the parent equation still says 0. Time reappears as a convenience inside particular regimes, not as a fundamental river. There's a guardrail we need to keep in place. Saying H psi doesn't mean nothing happens. It means the allowed states encode all allowed correlations at once. Think of a still photograph of a flipbook that contains every page layered together. Slice it one way and you read one order of images. Slice it another, you get a different order. Physics demands that whichever slicing you choose, the correlations line up consistently. That consistency is what you experience as dynamics. Here's a micro story. A researcher stares at a pair of entangled ions late at night. One is her clock, the other is her system. She conditions on the clock's state and plots the system's statistics. A sinusoid appears, oscillation without an external time parameter. She doesn't celebrate, she writes, "Motion is relation," and underlines relation twice. Critics ask, what about the arrow we feel? If time is relational, why does yesterday feel different from tomorrow? Relational time doesn't answer that by itself. It tells you how to order changes without a master tick. The arrow needs something else, a boundary condition that biases records in one direction. That's where entropy and the low entropy past enter, which we'll face soon. For now, the lesson is narrow and sharp. Fundamental equations can be timeless while still producing the appearance of evolution. The turning point is simple to state and hard to absorb. If time emerges from entanglement and internal correlations, then the glitch we've been chasing isn't a crack in a flowing river. It's the realization there was no river to crack. There are only patterns that can be sliced into stories that look like flows. And if the stories depend on clocks we build from the world, then the arrow we feel will depend on how those clocks line up with disorder. That's our next step. The arrow we feel, entropy and records. While the timeless equation pulled the clock from under us, something stubborn stayed put, the arrow we live by. Coffee cools, eggs scramble, hard drives fill with photos of yesterday, not tomorrow. If time isn't a river, why does it still feel like one? Here's the stake. Our sense of past and future must come from structure, not from a cosmic tick. Start with Boltzmann's blunt insight. Macrostates like warm coffee in a room can be realized by many microscopic arrangements. Cold coffee plus a warm room has more ways to arrange its molecules than hot coffee plus a cool room with the same total energy. Systems drift from less probable macrostates to more probable ones because there are overwhelmingly more ways to be disordered than ordered. That drift is entropy rising. It isn't a force, it's counting. Now remember, counting alone doesn't pick a direction unless you start from an improbable place. That's the low entropy past hypothesis. The early universe was in a remarkably smooth state. Matter and radiation spread nearly uniformly, with tiny ripples. Smoothness sounds like disorder, but in gravity, it's low entropy. Clumping galaxies, stars, black holes opens up far more microconfigurations. As the universe expands and gravity amplifies clumps, entropy rockets upward. That sets the stage for arrows to align. What actually happens in your day is a chain of record making. A record is a stable correlation. Bits on a drive, ink on paper, synaptic changes, a crack in a plate. When entropy rises, energy flows make it easy to create new records that point toward lower entropy states and hard to create reliable records that point forward. Your brain encodes memories by burning energy and increasing entropy locally. Those memories reliably reference earlier conditions because there were fewer micro-possibilities then. Tomorrow has many more compatible microstates than yesterday, so reliable memories of the future don't form. Here's the impact. The psychological arrow, the thermodynamic arrow, and the computational arrow line up. You remember the past because you're built out of processes that exploit free energy to write durable correlations about earlier, lower entropy macrostates. You don't remember the future because there's no narrow, low entropy funnel constraining it into a small set of microhistories you could stably encode now. Flow is your memory updating as entropy rises. Meanwhile, something else sharpens the edge. Loschmidt's paradox asks, if microscopic laws are reversible, why doesn't entropy sometimes go down? In principle, you could reverse every molecular motion and watch a shattered glass reassemble. In practice, you don't. The reason is practical irreversibility. To reverse, you'd need to control astronomical details with impossible precision. Any tiny mismatch pushes you back onto the overwhelmingly larger set of states where entropy increases. The arrow isn't in the equations. It's in the boundary conditions plus the statistics of large systems. There's a cosmic layer to the story. Roger Penrose argued that the early universe's gravitational field was extremely special, low in Weyl curvature. constraining the initial state so tightly that entropy had room to climb for billions of years. You don't need to buy every part of that hypothesis to feel the pressure it applies. Some condition made the early universe simple enough that complexity could grow and records could proliferate. Without that simplicity, there'd be no reliable arrows, no chemistry as we know it, and likely no brains to complain about it. Guardrails matter here. Saying entropy rises doesn't mean nothing ever runs backward locally. Fluctuations happen. Tiny subsystems can buck the trend briefly. Refrigerators export entropy to cool a compartment. Maxwell's demon looks clever until you count the demon's memory and erasure costs. When you include the full bookkeeping, device, environment, measurements, resets, the upward drift returns. The second law isn't a law of each molecule. It's a law of overwhelmingly likely histories given the initial condition. Here's a micro story. A data center tech swaps a failing drive. The old platters hold logs of last night's traffic, stable records of past packets. No drive anywhere holds tomorrow's logs. The reason isn't superstition, it's structure. The routers, the servers, the cooling systems run on gradients that let them fix bits about earlier network states. There's no gradient that can reliably fix bits about states that haven't been selected by dynamics yet. And this ties back to our glitch. In the block, all events exist, but you experience a direction because records accumulate one way. In delayed choice and quantum eraser experiments, the past that matters for interference is about which correlations are available, not about an immutable tape. When which path information is recorded, by a detector, by the environment, interference fades. When that information is made unavailable in the joint correlations, interference reappears in the sorted data. The arrow and the availability of records are linked. Here's the turning point. The arrow is not a river you float down. It's the bias in how records get written as entropy climbs from a special beginning. Your now is the leading edge of a growing network of correlations. That's why becoming feels real. You're the subsystem updating, not the universe ticking. But if records define the past, then quantum experiments that tamper with records can scramble what patterns look like, without rewriting what was registered. That's where we go next, into erasers that make the past vanish from one ledger while leaving another intact. Quantum erasers and the vanishing past. Here's where it gets slippery. In delayed choice quantum erasers, the past you think you saw can vanish from one ledger and reappear in another, depending on which correlations you keep. The stakes are sharp. If erasing which path information restores interference even when the erased choice is made late, then what happened isn't a fixed tape, it's a structure of available information. That pushes on our sense of cause, memory, and what a record really is. What actually happens starts with entanglement. Take a photon headed into a double slit or interferometer. Instead of letting it interfere cleanly, you entangle its path with a partner photon, an idler. The signal photon goes to a screen. The idler takes a different route through a device that can either reveal which path information or erase it. Crucially, the decision about the idler's path can be made so late that, in ordinary language, the signal photon has already hit the detector. On the screen, if you look only at the raw positions of the signal photons, you don't see interference. You see a smeared distribution. No surprise there. Entangling path information tends to kill interference because the environment, here, the idler subsystem, holds which path clues. The twist arrives when you bin the signal detections into subsets based on how the idler was measured. Sort the signal events according to idler clicks that erase which path information, and boom, an interference pattern appears in the conditional subset. Sort according to idler clicks that reveal which path info, and the interference vanishes in that subset. The immediate impact is easy to misread. It's tempting to say, we changed the past. But look at the guardrails. The screen's raw data never change. Every dot landed where it landed. What changes is the pattern you can extract when you correlate those dots with idler outcomes. You don't alter yesterday's records, you alter today's grouping of them. It's like having a shuffled deck already dealt face down. Whether you reveal a straight or a mess depends on which cards you turn over and how you sort the hands afterward. Let's put numbers to the feeling. In a canonical quantum eraser, the idler interferometer has two settings. In one, the paths remain distinguishable. Different detectors correspond to different slits. In the other, the paths are recombined so that which path information is erased. The signal's raw histogram is a flattish bump either way. But when you condition on the idler's erased clicks, the signal positions line up into fringes and anti-fringes, shifted interference patterns in the two complementary bins. Add those bins together and the fringes cancel, giving back the raw bump. Nothing spooky traveled back in time. The correlations were sitting there, waiting for you to ask the right joint question. Meanwhile, something else is happening in the students' heads. They stare at the screen and swear the interference came back after the fact. A veteran says, "Check the joint data." That sentence is the culture of quantum labs in 5 words. What counts are the correlations you can consistently record. If which path information is available anywhere in the joint system, idler, environment, a stray photon tap, interference can't show up in any unconditional statistics. If you block, scramble, or erase that information so it can't, even in principle, be recovered, interference can reappear in the conditional slices. Here's a micro story that anchors it. A team runs the eraser overnight. In the morning, before looking at idler logs, the signal screen looks boring. Then they load the idler file and plot the signal positions conditioned on detector D1. Fringes. Condition on D2. Anti-fringes. Their advisor marks the axis with a Sharpie and says, "Patterns are about questions." Nobody pretends they rewrote history. They learned which questions the data can answer without contradiction. The guardrails tighten as you push the timing. In delayed choice, erasers, the idler route is long, so the choice to erase or mark can be made after the signal detection is registered. The order doesn't rescue or doom the effect. The no signaling theorem still stands. You cannot use the eraser to send messages to the past because the signal side alone always looks like noise. The interference lives only in the joint, sorted data. If your friend at the signal screen tries to guess your idler setting, they'll fail every time until you call later and share which events to compare. But there's one problem we have to face honestly. Language wants to tell trajectory stories. The photon went through both slits until, or it took a path and then we erased the tag. The math refuses both as universal narratives. In setups tuned for interference, assigning a definite path creates contradictions with the observed fringes in conditional data. In setups tuned for which path, asking for interference is the wrong question. The eraser doesn't let you have both at once. It lets you pick which consistent account you can build by managing which correlations survive. The impact ripples outward. The past that matters in predictions is the past encoded in accessible records. If a would-be record, like which path information, is isolated, amplified, or broadcast to the environment, it hardens and kills interference. If that information is scrambled into global degrees of freedom so no feasible measurement can retrieve it, interference can return in principle. The experiment teaches a blunt lesson. Availability of information, not calendar order, decides which narratives physics supports. Here's the turning point. We didn't change what was registered. We changed which correlations we honored and which we destroyed. That's the vanishing past, not erasure of facts, but the collapse of certain stories when their supporting records are gone. And it sets us up for a bigger leap. If patterns depend on correlations, what if spacetime itself is a pattern woven from them? If that's true, then before and after might be bookkeeping, not bedrock. Next, we test that idea where geometry and entanglement start to blur. Spacetime from entanglement, equals tensor networks. While erasers were teaching us that patterns belong to correlations, another idea was forming in gravity's backyard. What if spacetime itself is made from entanglement? Not metaphorically, mathematically. The stakes are huge. If geometry is woven from quantum correlations, then distance and before-after aren't primitive. They're bookkeeping that emerges when enough entanglement lines up the right way. Here's the action that sparked it. In the late 199s, a bold duality linked a gravity theory in a bulk spacetime to a quantum field theory living on its boundary, at SCFT. No gravity on the boundary, full gravity in the bulk, yet the two descriptions match. Then a clean formula appeared, the Ryu-Takayanagi relation. It says the entanglement entropy of a region on the boundary equals the area of a minimal surface anchored to its edges, measured in the bulk. Translate that. How entangled the boundary degrees of freedom are tells you the area of a bulk surface. Entanglement doesn't decorate geometry, it measures it. The impact was immediate and unsettling. If area tracks entanglement, then cutting entanglement literally cuts space. Dial down correlations between two boundary regions and the minimal surface area shrinks, bulk connectivity weakens. Crank correlations up and the surface swells, connectivity strengthens. Space becomes elastic under quantum information. That hinted that geometry might be an emergent map of who is entangled with whom, not a stage where entanglement merely occurs. Meanwhile, something else was happening in theory rooms that made the picture visual. Tensor networks, MERA, PEPS, and friends, were invented to efficiently approximate quantum many-body states. They're graphs of tensors connected by legs. Entanglement flows along the connections. Build the right network and its geometry mimics a curved space. The number of legs you cut to separate a region scales with its entanglement entropy. Draw MERA for a scale invariant system, and you get layers that look like discrete slices stretching into a bulk. Without meaning to, condensed matter tools produce toy models of how space could arise from entanglement patterns. Here S where it gets wilder. Maldacena and Susskind proposed equals Epper. Einstein-Rosen-Bridges wormholes are the geometric avatars of EPR entanglement. Take two black holes prepared in a precise entangled state. The bulk description includes a wormhole connecting their interiors. No, you can't travel through it or send messages faster than light. The bridge is non-traversable. The point is structural. Entanglement builds connectivity. Separate systems joined only by quantum correlations can be adjacent in the right emergent geometry. Skeptics asked for stress tests. Hollow codes, quantum error-correcting code models stepped in. They showed that bulk information can be redundantly encoded in boundary degrees of freedom. Lose a few boundary qubits and you can still reconstruct bulk operators. That's error correction. The minimal surface in Ryu-Takayanagi acts like the boundary of what's reconstructible, the entanglement wedge. This wasn't poetry, it was machinery. Geometry behaving like an error-correcting code explained why the bulk can be robust to small boundary damage, and why locality in the bulk can emerge from non-local boundary degrees of freedom. Guardrails, though, add SCFT is clean in anti-de Sitter space with negative curvature. Our universe looks closer to de Sitter, positive curvature with a cosmological horizon. Extending these ideas to our cosmos is active, messy work. Tensor networks are discretized toys, not literal spacetime. Equals Epper lives best in carefully tuned states. Generic entanglement doesn't guarantee a nice bridge. Still, the pattern keeps reappearing. Entanglement dictates which bulk regions connect, which areas grow, and which operators you can reconstruct. Here's a micro-story that carries the human arc. A grad student staring at a MERA diagram draws a loop around a boundary segment and counts the bonds she'd cut. She calculates the entanglement entropy and watches her count match the theory. Her advisor adds a bond, entropy rises. He erases a bond, entropy drops. They aren't sculpting clay, they're sculpting space with correlations. Now remember the glitch we're chasing. If where is organized by entanglement, then when might be too. In add SCFT, time evolution on the boundary corresponds to motion in the bulk. Scramble a boundary state, entangle it rapidly, and the dual black hole interior grows. The Einstein-Rosen bridge lengthens. That's a clock made of complexity and correlation growth. Lloyd, Susskind, and others push the idea that computational complexity of the boundary state tracks the volume or action of certain bulk regions. As complexity increases, interior geometry expands. Flow looks like the growth of structured entanglement. The immediate payoff is conceptual. It explains why no global, observer-independent time has shown up. If the distance between events depends on correlation structure, then before and after are partly about which subsystems can serve as clocks for which processes. Relational time from Section 8 slides neatly into an entanglement first picture here. Clocks are subsystems whose correlations with the rest grow predictably. Geometry is the larger web that those correlations build and inhabit. We need one more guardrail. None of this grants shortcuts for messaging or time travel. The same theorems that protected no signaling in entanglement protect causality here. Non-traversable wormholes don't let you send a note to your past self. Tensor networks that mimic geometry still obey quantum mechanics. They don't break it. The magic is emergence, not violation. Here's the turning point. If space is entanglement and interior growth is correlation growth, then the era we feel and the when we assign are properties of an evolving information network, not beads sliding along an external timeline. That folds everything we've seen, delayed choice, indefinite order, relational time, into one clean statement. There is no global, observer-independent temporal order underneath the correlations. The order we use is the one that makes the entanglement web easiest to describe. To test that, we'll need clocks we can put into superposition and entangle on demand. Clocks that don't agree, superposition in timekeeping. While that was unfolding in gravity's backyard, clockmakers were doing something gutsy, putting timekeepers themselves into quantum states. Here's the stake. If a clock can tick in a superposition of rates or sit in two gravitational potentials at once, what's a moment supposed to mean? Timekeeping stops being absolute and turns into a property of states and relationships. What actually happens starts with the simplest clock, a quantum two-level system, an atom whose internal energy difference defines a frequency. Drive it and its state oscillates. Count those oscillations and you've built a clock. Optical lattice clocks trap thousands of atoms and compare their ticks to parts in 1080. That's like losing 1 second over the age of the universe. With that sensitivity, minuscule effects, motion, gravity, even quantum coherence matter. Now remember general relativity's prediction. Clocks tick slower deeper in a gravitational field and slower when they're moving. In 2010, NIST measured gravitational redshift across a 33-centimeter height difference, time dilation over a foot. With new optical clocks, groups have pushed that to millimeter scales. Slide a clock up a lab bench and its tick rate changes. No global time, just proper time along each world line. That's the classical setup. The quantum twist is letting the clock be in a superposition of paths with different tick rates. Enter the quantum clock interferometer. Put an atom in a spatial superposition, two paths at slightly different heights, while its internal state ticks like a pendulum. Because gravity redshifts time, the internal phase accumulates at different rates along the two paths. Recombine the paths and the interference fringe shifts by an amount tied to the tick rate difference. That shift is a direct signature of time passing differently in the two branches. It's not poetry, it's a phase you can measure. Teams have realized versions of this with atom interferometry and trapped ions. In trapped ion platforms, the clock degree of freedom, say, an optical transition, entangles with motion. Prepare the ion so its internal state evolves while its position wave function splits and later recombines. The visibility and phase of the interference depend on the internal ticking along each branch. Keep coherence, and you read out a gravitationally induced time difference without committing to a single trajectory. Lose coherence, and the clock story blurs with it. Here's the impact that hits metrologists in the gut. Precision limits shift when your clock is quantum. Entangling multiple clocks, spin-squeezing ensembles, GHZ states, reduces noise beyond the standard quantum limit, pushing toward the Heisenberg limit. You don't just average ticks, you correlate them so that uncertainty cancels more efficiently. Those entangled clocks become better rulers for tiny gravitational potentials and weak forces. Timekeeping turns into many-body physics, where the best time is a property of a collectively prepared state. Meanwhile, something else is happening as we marry relativity to coherence. If an atom's center of mass is delocalized in a gravitational field, the proper time along its branches differs. That difference can entangle the internal clock with the path degree of freedom, which acts like a witch path tag and degrades interference. Seen from another angle, gravity induces dephasing between branches by making their internal ticks disagree. Preserve coherence long enough and you can watch the trade. Treat time dilation as both a resource and a decoherence channel, depending on what you call the system. Guardrails keep this grounded. No one is sending messages to the past with a fancy wristwatch. These are tiny effects in tightly controlled setups. The superposition of tick rates lives for microseconds to seconds, not hours, and interpreting results demands care. The phase you measure is a relative phase between branches, not a stamp from a cosmic clock. Still, the conceptual bite is sharp. If two branches of one clock disagree on elapsed time, what time is it? Becomes a question with a state-dependent answer. Here's a micro-story. A researcher babysits two strontium lattice clocks through the night. One sits on a granite slab, the other rests a centimeter higher on a vibration platform. She phase-locks lasers, counts beats, and watches the fractional frequency shift creep into significance. When the data clear the noise, she texts, "We moved time by half a fingernail." Her friend replies with a yawning emoji and, "Welcome to relativity at home." Push it further and you get clocks in superposition not just of place, but of gravitational potential using massive superposed systems. Proposals suggest creating mesoscopic superpositions and letting their self-gravity imprint phases on internal clocks, a path to test how gravity and coherence play together. We're not there yet, but each incremental step, better isolation, longer coherence, cleaner readout, tightens the dialogue between geometry and quantum states. Now remember our through line. We saw delayed choice undercut before, entanglement ignore distance, indefinite order melt sequence, the block erase a universal now, and relational time rebuild becoming from correlations. Quantum clocks close a loop. They show that even the devices we trust to label moments are just subsystems whose correlations can superpose, entangle, and decohere. A moment isn't a bead on an external string. It's the state of a clock correlated with the state of a system in a network that holds together, as long as coherence and stability allow. Here, the turning point to carry forward. If your best clocks refuse to agree when you force them into quantum games, then the hope for a single, observer-independent temporal order fades further. Timekeeping becomes a property of processes, not a backdrop. That sets the stage for our synthesis. The quantum glitch isn't about exotic paradoxes. It's the clean, testable fact that there is no global temporal order underneath the correlations we actually measure. The quantum glitch defined synthesis. We promised a glitch. Here it is, clean and sharp. There is no global, observer-independent temporal order underlying quantum phenomena. Not a hidden master clock, not a single before. Then after that, every observer and every process must obey. What we call time is a summary of correlations, a story stitched from records, clocks, and constraints. Here's why this moment matters. Causality is how we steer lives. We plan, we regret, we teach cause and effect to kids. If the bedrock lacks a universal order, do choices collapse into noise? No. The stakes are big because the fix is subtle. Causality survives as relations among records and interventions, not as a universal timeline. That move saves what we use while dropping what we don't actually have. Walk through the evidence chain. First, delayed choice and quantum erasers. They showed that late decisions about what question to ask determine which consistent account you can build about a photon's past. No messages to the past, no contradictions. just the blunt fact that what happened is the pattern supported by accessible correlations. Before and after didn't rescue you, joint data did. Then entanglement. Bell tests shut the door on local realism with independent settings, fast switching, and even cosmic randomness. The correlations didn't care which detector clicked first because first depended on who watched. Only data looked random. A with B data revealed structure. Time ordering didn't explain the link. The entangled state plus settings did. Next, indefinite causal order. The quantum switch put a right arrow B and B right arrow A into a coherent superposition and certified genuine causal non-separability with witness measurements. Certain tasks got easier when order melted, a practical gain from a conceptual crack. The lab didn't produce paradoxes. It produced interference between sequences, meaning what happened first wasn't a settled global fact. Layer on the block universe. Relativity erased a universal now and replaced flow with geometry. Your world line carries records, proper time is path length, not a cosmic tick. The block doesn't move. You update within it. That perspective didn't kill causality. It reframed it as constraints among events that hold in any slicing. Slide to the timeless equation. The Wheeler-DeWitt constraint, H psi, stripped explicit T from the master description. Page, Wooter's relational time put becoming back as conditional structure. When the clock subsystem reads X, the rest looks like Y. Experiments with entangled clocks showed the idea can have lab teeth. Again, order came from correlations, not from an external metronome. Now fold in spacetime from entanglement hints. In holography, areas track entanglement entropy, and interior growth mirrors correlation growth and complexity. Tensor networks built space from bonds. equals epper-tied connectivity to entanglement without granting shortcuts. If where is correlation structure, it's natural that when is too. Clocks are just subsystems whose correlations with others change predictably. Finally, quantum clocks in superposition. When tick rates differ across branches and entanglement turns timekeeping itself into an interference pattern, you learn the quiet lesson. A moment is state-dependent. Ask what time is it, and you'll get an answer tied to a clock system relation, not a universal label. Put these together and the glitch stands. Physics gives you a consistent web of correlations, plus rules for how interventions change expected statistics. It does not give you a single, objective temporal order that explains all correlations. Causality becomes relational, about which interventions can influence which records, without reducing to earlier pushes later, in a way everyone must agree on. Guardrails clearly. We are not claiming you can message your past self, break no signaling, or pick outcomes by willpower. Delayed choice doesn't rewrite registered data. Entanglement doesn't carry signals. Indefinite order doesn't spawn paradox. The block doesn't erase agency. Wheeler-DeWitt doesn't mean nothing happens. Holography doesn't make our universe ad s by fiat. Quantum clocks don't turn wristwatches into time machines. The glitch is narrower and stronger. No global order lives underneath the correlations. The order you use is contextual, relational, and often emergent. So what about free will and responsibility? Here's the human angle. Freedom doesn't need a cosmic timestamp. It needs counterfactual control within a model of you as a physical subsystem. When your brain-body dynamics can steer which reliable records get written, given your values, information, and constraints, you exercise agency. In a relational picture, I could have done otherwise means in nearby states consistent with my history and physiology. Different interventions were open and would have produced different records. That's enough for ethics and law, which already operate on records and counterfactuals, not on metaphysical clocks. Here's a micro story. A scientist chooses to replicate a surprising result instead of chasing a flashy new idea. Months later, the replication fails and saves a field from a false start. In the block, both paths exist as possibilities. On her world line, the records show care, not luck. Agency lives in that record making, not in a hidden tick that stamped her choice as first. There's one unresolved piece we won't fake, the low entropy beginning. Everything about arrows and records leans on a special boundary condition that made reliable memory possible. We've reframed the puzzle, not solved it. That open thread matters because it sets how strongly the arrow bites. The payoff you can bank is practical. Think in correlations. Design experiments around which records survive and which questions remain consistent. Treat clocks as tools, not as the truth. When order helps, use it. When it fails, switch to process language, interventions, constraints, witnesses, wedges, complexity. That's how you navigate a world where time doesn't rule. So what do we do with a life lived inside this glitch? We live it. We optimize records, shape branches, and build meaning in the network that actually exists. Then we face the arrow with eyes open. Living without time's river, applied meaning. So how do you live when the river isn't real? You switch from moments to records. The stake is personal, regret, anxiety, meaning. If now is a slice where records update, your leverage is over which records you help exist. You don't chase time, you shape correlations. Actionably, think in state changes. Optimize processes that leave durable, shareable traces aligned with your values. Conversations, code, care, craft. Sleep and attention become engineering choices for reliable record making. Nostalgia softens when you realize you're comparing today's messy distribution to a filtered memory of a low-entropy past. The fix isn't to rewind, it's to write better records now. Impact shows up in resilience. Anxiety often forecasts futures with no width. In our frame, futures are distributions you can steer by changing inputs, skills, teams, protocols. You gain agency by improving model quality, feedback speed, and error correction. You aren't moving through time, you're moving through states with different information. A micro story. A physicist misses a flight, wanders into a colloquium on entangled clocks, and hears the seed of her next project. The accident is just one branch where a record formed. She nurtures it, emails the speaker, drafts an experiment, recruits a student. Months later, a paper lands. She didn't bend time, she amplified a correlation. Guardrails hold. Science stays empirical. Ethics doesn't evaporate. Responsibility is about counterfactual control over records you influence given constraints. Freedom is selecting interventions that steer robust outcomes, not violating physics. Payoff, meaning is record alignment. Choose habits that make your preferred branches thick, redundant, resilient, widely shared. That's how you live well in a block and feel flow without worshiping it. Time doesn't flow, correlations do, and we ride their growth, mistaking updates for a river. If you want the sequel, where geometry itself emerges from entanglement and complexity, watch the next video right now. Subscribe to Cosmic Ventures for true cosmic stories where experiments lead, myths don't, and your curiosity gets better records.